Welcome everybody. Let's talk about how we're going to calculate the pH of a solution that contains either a strong acid or a strong base. So the first thing to keep in mind with this type of a problem is that if you have a strong acid or a strong base involved in a chemical reaction, whether it's a dissociation reaction or later when we talk about reactions between acids and bases, if there's a strong acid or a strong base present, those reactions are going to go to completion. So for today, we're talking about what happens when we put those acids or bases in water. What is the pH of that solution? So we're going to start by writing a dissociation equation, and then we're going to use stoichiometry to figure out what the concentration of hydronium or hydroxide ion that will result will be, and from there we'll be able to calculate the pH and or pOH. So let's start with an example. We've got some 0.0010 molar HCl. So if we imagine what this is, we've taken hydrochloric acid and we've placed it in water. And this reaction between hydrochloric acid and water is going to go to completion. So I'm going to use a regular reaction arrow. And all of the hydrogen ions are going to get transferred from the HCl to that H2O because it is a strong acid. And so I'll end up with the hydronium and the chloride ion. If I were to imagine what was going on in a beaker picture or particle visualization, I would have had all of the HCl break down and form chloride ions. So you don't have any of the original acid remaining. With that in mind, we are going to make an ice table because I want to use concentrations, but we're not going to set up equilibrium. We're actually going to have what is a limiting reactant problem. Here we just have an excess of water. There's tons of water in this beaker compared to everything else. So it's certainly not going to limit the amount of hydronium that we can make. All of that HCl is going to dissociate, forming hydronium ion. And so if my goal is to calculate the pH, I know that the pH is the negative log of that hydronium ion concentration. And so I'm just going to be able to plug in the value of hydronium, since I worked in concentration, directly into my pH equation. It's worth noting from a significant figure standpoint that the concentration that we were given had two significant figures. And if you recall, we talked about in class how if you have a logarithmic value, the only digits that are significant are the ones that are after the decimal point. And so there are two significant figures in the value 3.00 for that pH. To calculate the pH of a base solution, it's going to be very similar. We're, of course, going to start by writing our dissociation equation for what happens when we put the base into water. And I know we're dissolving our base in water, but recognize that the water doesn't actually change anything in the way we write the equation. And so generally speaking, we won't take the time to write the water in that balanced chemical equation. Once again, I'm going to choose to work in molarity here just to make my life a little bit easier. And since this is a 0.020 molar barium hydroxide solution, I know that my initial concentration of barium hydroxide in that imaginary second before it dissociated was 0.020 molar. And again, this is a strong base, so it's all going to dissociate. And taking into consideration the mole ratio in that balanced chemical equation, I know that my concentration of hydroxide after the dissociation occurs is going to be 0.040 molar. So from that, I'm actually going to be able to calculate my pOH. And once I have my pOH calculated, I can calculate the pH, because remember that pH plus pOH always have to add up to 14. So I'm going to get a pH of 12.60, and once again, I had two significant figures in my starting concentration, and so I want two significant figures in my final answer.